Well, we're going to do one more example where we're given the differential equation and the solution, and all we're asked to do is verify. And then after that, we'll actually solve a differential equation. So here we have x equals radical t squared plus 1 minus 1. Show that that is the solution to this differential equation. X prime is t over x plus 1, and the initial value, that's a semicolon, at time 0, x is equal to 0. So we're just going to verify that that's the solution. So if that's the solution, in order to plug it in, here's x, but we also have an x prime, so we have to take the derivative of this, which I wrote out for us. T squared plus 1 to the 1/2 is the derivative is 1/2 t squared plus 1 to the negative 1/2 times 2t. And I'm going to simplify that, and then we're just going to verify that this is true. Well, first, I guess we could just verify right now that this is true. If t is a 0, you get x equals radical 1 minus 1, and that's equal to 0. So that part we've already verified. So let's see, x prime. I'm going to simplify that a little bit. 2 times 1/2 is a 1. So I'm going to write this like t. And instead of times t squared plus 1 to the negative 1/2, I'm going to write over t squared plus 1 to the positive 1/2. So what I just wrote is equivalent to that. Equals. Okay, so t over. So this, I'm just going to take it and write t squared plus 1. And I want it to have a minus 1 there, so I'm going to put minus 1 plus 1. And then notice that this happens to be x. I left off the 1/2 right here. This is just x. So that's equal to t over x plus 1. So very simply, we showed that this really is the solution to that differential equation. All right, now let's solve a differential equation. You don't need to memorize how to solve this, but you're going to need this information for one of your homework problems. All right, this happens to be the standard form for a first order linear ordinary differential equation in the variable y. So if it were in the variable x, you just replace the y's with x's and probably the x's with t's. So here's the standard form. Coefficient of 1 in front of the derivative term plus some function of x times y is equal to some function of x. And I'm going to go ahead and solve this equation and show you how to do it step by step. So notice that this is already written in this correct form. dy dt, we're doing dy dt instead of dy dx, that's no problem. Plus 0.4y is equal to 3e to the negative x. Convince yourself that that's, let's see, that needs to be e to the t, e to the negative t. Okay, so for us, this is a function of t, and this is a function of t. So we could even mark this as being p of t is the constant 0.04, and then this function right here is our f of t. Okay, so it looks like I already started incorrectly. The integrating factor is simply e to the integral of p of t dt. Okay, so I took e raised to the integral of p of t is just the number 0.04. So all I did here is, what is the integral of 0.4? The integral of 0.4 dt is just 0.4t. So This is our integrating factor. And what we do is multiply both sides of this equation by the integrating factor. So we get e to the negative 4, or to the positive 4t times dy dt plus 0.4y is equal to 3e to the negative t times e to the 0.4t. We're not going to spend a lot of time explaining why this works, but you'll see why it simplifies things greatly. It turns out that the left-hand side now greatly simplifies. It is equal to, I'll write what it's equal to, d dt of the integrating factor times y. So the integrating factor was e to the 0.4t y. Why is that nice? Because the next step is going to be integrating both sides. All we have to do is get rid of this, and it's integrated. And then what's this going to be? A 3e to the, that's a negative 1t, that's a 0.4t. Add those coefficients, the negative 1 and the 0.4, and we get a negative 0.6t. So that's all we're going to have to integrate, and that's step 3. Integrate both sides and solve for y. So I'm going to do the step 3 up here. Integrate both sides with respect to t, of course, and then solve for y. So it's quite simple. So the left-hand side is just e to the 0.4t y. And that's equal to the integral of, I'm going to put the 3 in front of the integral, e to the negative 0.6t dt. So all we are doing is integrating both sides. I've already successfully integrated the left-hand side, and now we need to integrate the right-hand side. So e to the 0.4t y is equal to this times e to the negative 0.6t divided by, or multiplied by, negative 1 over 0.6. Yeah, negative 1 over 0.6. So then we get a 3 over 0.6, which is going to turn into be a 30 over 6, a 5. So e to the 0.4t y is equal to, multiply this and this, and we get a negative 5 e to the negative 0.6t. And I guess let's see. I guess when I did that integration, I left off a constant. You only need to put a constant on one side when you're integrating both sides. So I'll put that constant there. And now I need to multiply both sides by what to get y by itself? That would be e to the negative 0.4t. So that would be, I'll just make a note that I'm multiplying both sides by e to the negative 0.4t. So therefore, when I add these together, I'm going to get e to the 0, which is 1. And then I'll multiply it over there as well. So y is equal to negative 5, let's see, e to the negative 0.6 times negative 0.6 plus 0.4, and they're negative, would be just a negative 1. And you have to multiply the constant as well by e to the negative 0.4t. That's the general solution. I'm going to go ahead and circle it. We're not quite done. The only thing we don't know is what c is, but the initial value is that y of 0 is equal to 5. So that implies that y is a 5 when t is a 0. So when t is a 0, I'm going to get a negative 5, and that's going to be a 1, plus c. And when t is a 0, that part's going to be a 1. So c is just going to be 10. And that gives us the solution. This time I'll write it like y of t equals negative 5 e to the negative t plus 10 e to the negative 0.4 t. Okay, so that is the solution, and you may need that in your homework. And why is that? You're going to be dealing with this differential equation again, and you're going to have to compute the value of y at some value of t. And you're going to use a numerical method to do it. So it's going to be an approximation. Say we need the value of this function at y equals 12. Well, you're going to do the numerical method to estimate it. And if you want to compute an error, you're going to need to know the exact value, and you would plug it into this function.